Hello, Calc. We're looking at this. It's being made on the 21st. It should be up and available to you. That's the Monday on Thanksgiving break. So I promised you it would be up, but probably not before Monday. And so it is. So I'll be putting that up a little later. And the date is the 21st. So sometime during this week, view this video. We missed you, Joel, on Friday where we had our smoothies. We made pumpkin smoothies and we made strawberry fruit smoothies. So we hope to repeat that when you're there sometime. It was a bummer that you were feeling poorly that night and day. All right, hope you're back to normal now. Okay, we are at a point where I want to discuss the first and second derivative test. Seems like we're kind of stuck there now for a while. We had a test in between. So let's go ahead and look at the first and second derivative test again. So let me go ahead and write out the first derivative test for your viewing pleasure. I believe it's in your notes. If not, get it into your notes. So the first point about the first derivative test is, I'll get in there just right. If the first derivative changes from negative to positive at some point C, then the function has a relative minimum at that point, C, comma, f of C. So we're looking for a derivative that goes from negative, so a negative derivative would have a slope like that, and then it'll go to 0, and then a positive derivative. So it should make sense to you that the first derivative is changing from negative to positive, to 0 to positive. So that should identify a relative minimum. All right, so in words, the other way, if the first derivative changes from positive to negative, and at C, then f has a relative max. So we have the opposite. First the derivative is positive, then it's 0, then it's negative. So we're expecting a maximum, relative maximum at that point. And lastly, we can conclude, point 3, if the first derivative is positive on both sides of C, or negative on both sides of C, then f of C is neither a relative min or relative max. So if it was positive on both sides, it would look like something like this, then it would zero out, and then it would become positive again. So I called that an uphill rest. And if it was negative, we would do something similar, but with a negative sloping line. Negative sloping, 0, and then negative sloping. So at these points, we do have a 0 first derivative, but we do not have a max, relative max, or a relative min. All right, so that's the first derivative test. If for some reason you don't have it written in its formal way, like this is, then go ahead and write it in there now. All right, pause and write, and I'll go on. So, all right, let's look at let's go ahead and let me just use this paper, this blank paper here. Let's look at an example for just the first derivative test again, just to bring it all back to mind. So if we have f of x equals x squared minus 4 to the 2/3, if that is our function, I want to know where it has a relative max and a relative min. So where do I look for those places? So first of all, we're going to find the critical points, and the critical points are the candidates for local max and mins. So to do that, I want to know where the first derivative either doesn't exist or equals 0. So let's go down that route. So the first derivative of this function right ahead of me, I'm kind of slowing down so you can get ahead of me. Alright, so 2/3 times something raised to the 2/3 minus 3/3, which is a negative 1/3, times the derivative of that something. Our favorite chain rule. Let's clean it up a little bit. So 2x and 2 give me a 4x in the numerator. And in the denominator, I have a 3, and that stands for a cube root of x squared minus 4. I want to set that first derivative equal to 0, and that will tell me where the critical points are, and I also want to look where that doesn't exist. So, when we have a rational expression like this, where there's an algebraic expression in the numerator and the denominator, we know that the whole fraction will zero out when just the numerator zeroes out. So I'm going to isolate that, or perhaps you can think about it more algebraically in that if I multiply both sides by this identical denominator on both sides, it disappears from the right and equals 0 on the left. So we end up with 0 equals 4x. So 0 equals 4x, looking at that, that yields x equals 0. So that is where this whole expression will be 0 and is a critical point. Is there a point that will cause this expression to not exist? And there is, wherever the denominator is 0. So inspecting that, what value in here would cause a 0 when I take the cube root of the 0 will be 0 times 3 is 0. So I'm going to inspect in here, and when will that be 0? Well, that equals 0 when x is plus or minus 2. So by inspection, I found 3 critical points. 2 where the derivative does not exist, and where the denominator is 0, and 1 where the whole expression or the numerator equals 0. So I like to make a little map of this. Call it a sign line, S-I-G-N. A sign line is basically a number line. Let's indicate what it is that I'm mapping on this line. So I'm going to map f prime. That's what I'm talking about here. So I'm going to actually put that on the line, and as I do that, I'm going to put in these points of interest. Minus 2, 0, and positive 2. These are where the derivative is 0, so I'll indicate this. So below the line, I have my x values. Like, I didn't put in 1 because it's not all that interesting to me right now, but these values are the x values. These values are the derivatives. Notice the derivatives, that's not exactly right, is it? Derivative didn't equal 0 here. It was do not exist. So I don't want to mess up on that again. So do not exist at negative 2 and 2 and equals 0 at 0. So those are the critical points. We're always going to start there. Now the first derivative test told us to look to the left and the right of these critical points, test points, and see whether the derivative is going from negative to positive or positive to negative or neither. So let's see what that yields. So I have to test a value in this side, so probably the easiest is to test minus 3. So where do I put that minus 3? That minus 3, we are on first derivative land here, so we want to test minus 3 in the first derivative. So that's right into here. So this is where I'm throwing all the values. And all I really need to know is if it was a positive value or a negative value. I don't need the exact value. So when I put a minus 3 in for x on the top, I get a negative number. So I keep that in my head. When I put a negative 3 in the bottom, I'm going to get a 9 minus 4, which is some positive. 9 minus 4 is 5. The cube root of 5 is some positive number, times 3 is some positive number. So I end up with a negative number divided by a positive number. So do you see where I don't spend a whole lot of time with that? I just need to find the value as far as its sign goes. So what should I test between 0 and -2? Test number 1, -1. All right, so when I plug that in here, similarly, I get a negative on the top, and on the bottom, I get -1 squared is 1 minus a 4. So I get a negative in here. Cube root of a negative number is negative. So looks like I have a negative on the top and the bottom. So I'm getting a positive in this interval. And lastly, not lastly, we got 2 more sections. Between 0 and 2, I'm going to test 1. And when I test 1 up here, get a positive on the top, and I get a negative on the bottom. That gives me a negative for that interval. And lastly, I'll test above 2, I'll test 3. And when I put that in here, I get a positive over a positive. All right, and you can slow that down and confirm it, but you'll see it is true. All right, so now I have a map of what the first derivative is doing at these intervals. All right, with those test points. So now the whole test is to find max and min, relative max and min, so they can only occur at critical points. So I want to know, from examining this, is this a max or a min, relatively speaking? So on this side, it's negative. So I'm thinking in my head, we have a negative sloping curve. At this point, it didn't exist, so maybe we have some sort of sharp point or whatever, and then it goes up positively. So this is a local min, and that should make perfect sense looking at the sign of the derivatives on either side of this -2. Moving over to the 0, what's happening here? Here it was positive, then 0, and then negative. So we have positive slope, 0 slope, negative slope. So we have a local max. And at this critical point, we have a do not exist. So it goes from a negative sloping, then some sort of sharp point, and then positive sloping. And that is, again, a local min. All right. It's not quite enough just to tell me the x values of the local mins and max. So we're going to improve on that. So we know there's a local min at -2 for the x value. So we're going to bring it home by finding the y value. So where do I put the -2 to find the y value? All right, it's in the original. So when I put a -2 up there and square it, you'll see that we end up with a 0. And here, this local max occurred at 0. So when I put a 0 up there in the original, I get the cube root of 16. Okay, cube root of 16. That'll do. And then over here, when I put 2 in the original, I get a 0 again. So these are the exact local and mins and max of this function. And I like to check the values, the graph, just to see if it makes sense with my outcome. I'm expecting a critical point at 0, -2, and 2. And some kind of maximum in between. All right, so let me just show you the graph. So it comes down and it hits -2 and rises sharply, goes up, and then hits 2 again sharply and goes up. So does that make sense to what we saw? Well, here is -2, 0. It's that we claimed it was going to be a local min, and sure enough, it is lower than the other values in that close by neighborhood. And same for 2, 0, right in here. And I imagine then this point is my my cube root of 16. So somewhere, what is the cube root of 16? Let me see. 16